Hello, everybody, and welcome back to Dr. Bob's Operation Get Good. How's it going? Week 4. Got a lot to go through, so let's go ahead and get started right away. So, one of the things I did last week is I forgot, and I did the wrong problem for the medium level problem on the video. So, I'm going to go ahead and go over that problem here. It's going to be pretty quick. So you have the wizard who gives you two integers n and k and selects a number from 1 to n, and you get k questions, and then you have to guess the number. So basically, the high-low guessing game or whatnot. And so the idea is the best you can do at any point is to cut the search space in half, right? So you just want to figure out if the log base 2 of the number n is at least as big as k. Now the problem with this, it does say one thing. These inputs might not fit into a 64-bit integer. Now this is not a problem for some languages, but it is a problem for others. So the primary way to get an edge in this one is to choose a language that has a big integer class. If you don't have that, C++ is the one notable exception. It doesn't really have one that's standard. Now, there is one that exists. There's plenty out there. But I don't think there's one that's just part of the standard template library. I could be wrong. They may have updated since then. But Python 100% has arbitrary precision integers by default. So all you had to do is input the line, split it into two pieces, n and k, and then what I did was I just divided by k. I divided n minus 1 by k as many times as I divided n minus 1 by 2 k times, and if it got me to 0, then I said true, otherwise false. Pretty simple. This, for those of you who are unaware of Python, double slash is integer division, because division by default produces floats in Python, even when it divides evenly. Okay, so next, let's get to the problems from this week. So we've got Loon's checksum algorithm. It says, it basically spells out the algorithm. It says, starting at the right end of n, transform every second digit. So starting at the right, transform every second digit by multiplying by 2, and if there's more than one digit, add the digits together. So basically, the numbers 0 through 4 end up going to 0 through 8. But the numbers 5 through 9 would go to 10, 12, 14, 16, 18. Instead, they're going to go to 1, 3, 5, and 9. So another way of looking at it is you take 2 times the digit and then add the digit divided by 5 integer-wise, and then take it mod 10, which is what I did. Then you add up all the digits. If it's divisible by 10, you pass the checksum test. So most credit card numbers meet this, and so it gives you some sample inputs, the number of runs, some numbers here. So one of the tricks is when you're doing this, you probably want to read these in as strings and not numbers, and then you can do the individual characters as numbers. So my submission looks like this. I grab the number of runs from the input. That's 3 in the sample input. Then I go through for the range, and I set my sum to 0. And then I use a variable here called double. Basically, that tells me whether or not I'm going to double and do the thing with the value. Then I grab the input for each line. Then I say for every character in the input, reversed. So going backwards. And then I say add to the sum. If double, we're going to add to the sum 2 times the int plus y, or 2 times y plus the y divided by 5. So it's the integer version of y. These are characters, so, or actually one character strings, but sure. This converts it to an integer. Now you'll note I didn't actually take it mod 10. And that's because mod 10 is, survives addition. So when I take it mod 10 here at the end, it's going to have the same result. Otherwise, we just add y, and then I flip the double. So we start by not doubling, and then we double, not double. We start from the end, go backwards. Okay. So that's pretty simple. The next 2 problems we're going to require a fair amount of detailed talk. So here we go. Prime path. So the idea is you've got the, quote, prime minister, lol, who has a prime number on his door, and they're going to change it, but he wants to make sure that as you post numbers over the numbers, you will never have a non-prime. And so the idea is, this is essentially another graph theory problem. The idea is every prime number from 1000 to 9999 is a possible number that can be on this door. And you can move from one number to another if they share exactly 3 digits. Okay? Now, the number of primes between 1,000 and 10,000 is about 1,080 or so. So, if you use Dijkstra's algorithm to do the pathfinding, Dijkstra's algorithm runs at about n squared time using a naive implementation, so you should be pretty okay. And that's what I did. This one I did in Java just to, 1, mix it up, and 2, because arrays and indices get along a little better in Java. So, for example, here you start with 1033, then you can go to 1733, 3733, 3739, 3779, 8779, and then 8179. So that gets you from point A to point B. You can see all of these values down here. 0, of course, is the distance from 1 to itself, or from a number to itself. And then you will look down here at the output and says 1 line for each case, either beginning with a number stating the minimal cost or containing the word impossible. I'm not quite certain it's impossible for any of them. I haven't actually checked to see if the graph is connected. I have no idea. But there's a few steps in this. First, you're going to want to extract a list of all of the primes. Just going to want to do that. Or all the primes you're relevant. So what I did is I created the ever so lovely prime_sieve function. This is using what's called the sieve of Eratosthenes. It's about, it's a quadratic algorithm. And it's not terrible for finding primes. You can usually, what it does is it returns a Boolean array, and the value, the true or false value at a given element of this Boolean array is true if the index is prime, false otherwise. Okay? So that's why when it's returned, it's called isPrime. and I set its length equal to A, so this returns all of the primes less than A, or a Boolean structure giving you that list. Now, the arrays, this fills it in with true. So you start with everything true except 0 and 1, you set those to false. Then you go through from 2 until the square root of A, essentially. So you go until multiplying I by itself would get you something bigger than A. The reason you do that is because once you reach the square root of the end of the list, you will have already marked off everything that's not prime. Because any number that is not prime has at least one factor less than its square root. Because the other factor must be greater. It's the other way around. So, we then check to see if the number I we're on is prime. So if it is prime, we're going to leave it prime, but then we're going to go to the next multiple of that number, so 2 times that number, and then go all the way to the end of the array, adding I at a time, setting them all to false. So once you set 2 to true, you can then mark off 4, 6, 8, and so on. Mark those all as false. You get to 3, you're going to mark off 6, 9, 12, and you're going to set a lot of them to false more than once. That's okay. We can do that. So then I have this thing, which is not the world's most efficient thing. Probably should just use an array list instead. That'll do things in amortized constant time. But this isn't that bad either. I basically go through, I count the number of values in the list. Begin with, then I just create an array of that length, the number of true primes in the list. Create an array of that length, and then go through and list them out. So we start with x is 0, so that's going to say, okay, the 0th prime is here. And as soon as we find the first prime, we're going to set x++. We're going to set the value at that location equal to the index where we found that prime. Now, this right here, x++, for those of you who don't know, what it does is it returns the value x and then increments it after the fact. So that's doing 2 things at once, really. I'm just saving space. All right, now this is Dijkstra's algorithm. So Dijkstra's algorithm is a algorithm for finding the shortest path between one source and all the other nodes in the graph. Now, if this was the first thing I tried, I would have done something a little different, but the way it is right now, it's set up to take an adjacency matrix of the graph. So the way that works is every node in the graph, or for every node in the graph, you're going to have a row and column of the matrix. And then if there is an edge from one to the other, there will be a 1 in that column. If the nodes are the same, so along the main diagonal, you will have a 0. If there is no node, you will have infinity. But I'm representing infinity with 10,000 because it's bigger than any path we'll ever find. So the way you do it is you start all of the distances at infinity, and you set the visited array to false, and then you go for the source. You start the distance of the source, you set that to 0, and then I also keep track of how many items I have visited. That way I don't have to sit there and check the visited array every time. And I say next equals source. So next is the value we're going to expand, or is the node we're going to expand next. So we make sure that we are we make sure that we haven't visited all the nodes, and that we're actually going to visit another node next. So this will end up being -1 if, for example, we haven't visited all of the nodes, but it's impossible to get from our set of nodes to another node. So this is how we handle the impossible case. We set current equal to next, so current becomes the one we're expanding. We go ahead and set that visited to true, add 1 to the count, and set next equal to -1. So the next one will expand. We're going to go through as we check the list to see what the next value should be. Then we go through the entire list of nodes. We check 1 if it's not visited. Then we check to see if the current distance to that node is greater than the distance to the current node. And keep in mind that this distance array represents distance from the source. Okay? So this distance of the current node to plus the length of the edge from the current node to I. So if it's greater than that, then we'll replace the distance I with that better distance. Now, in the event that there's not an edge, this will be 10,000, so it'll definitely be greater. It'll definitely be bigger than this distance. Then we want to find what will be our next value. So the next value you'll want to check at every step is the lowest distance unvisited node. So after we've updated this distance, perhaps, we check to see if next is equal to -1, or the distance to node I is less than the distance to the current next node. Now, I had to put this in here to make sure that we didn't try to compare it to a non-existent node. I just realized I think this is redundant. I think it's going to go to all the nodes regardless of whether you can actually reach it or not. We're just going to have infinite values there. Then I have this one real quick function to check to see if two variables are connected, or two numbers are connected. I get their string representations. I get their string representations and go through for each character, check to see how many are equal, and then if it's exactly 3, they're connected. Now, and then there's one other thing I do, and that is I create a reverse lookup list. So my first two functions up here were designed to grab booleans representing the primes and then grab a list of the actual prime numbers. Here, what I'm going to do is I'm going to create a list that tells me what index in the list each prime number is. So that allows me to go back and forth between these pretty quick. There's going to be a lot of -1s in this list, but we will never encounter those -1s. So here I just go through the entire list, n, and set the value at the index corresponding to the prime equal to the index in that original array. Alright, so finally, we get to the main function. I do the reading, and then I say, okay, first I'm going to get the list of primes. I'm going to call prime list with prime sieve as a argument, and I gave it a start and an end. My start is 1,000, my end is 10,000. So that gets me the total number of primes, or the total list of primes that are relevant, 4-digit primes. I then create the lookup list, and I create a graph. We're going to initialize the graph in this set of loops. We're going to say I go through for every I and j in the graph. If I is equal to j, so if they're the same, we want to set that value in the graph equal to 0. If they're connected, we set it to 1. Otherwise, we set it to 10,000, which is what I said earlier. Finally, we go through for each run. We read in the line, and then I call Dijkstra on k, and I say pass in the graph. I pass in the lookup value of the 0th of the first number in the input. So that lookup value, so the number in the input is the prime that we started with. I need to find out where that occurs in the list of primes so that I can find what node it corresponds to in the graph. That gets passed into the function, and the Dijkstra call actually ends right here. And then the next part is indexing into the array, because the Dijkstra function returns the entire array of distances from that spot. Because as I said, it returns the shortest distance from any node to all the other nodes. So then we find the node corresponding to the second prime and look up the distance to that node. If it turns out to be 10,000, we say it's impossible. Otherwise, we say the distance is k, and this solves the problem. It's a big mess of code, but every single one of these functions has a very specific purpose, and every single one of them, or at least these three up above, like the Sieve Veritasenes, the Dijkstra's algorithm, those are very strongly used algorithms. Now, if I had started using Dijkstra's algorithm to begin with, I would have instead used an adjacency list, so we wouldn't have to go through all the nodes every time to check to see who's visited, just the neighbors of the current node. But we would still then have to look up what the next node to check is. Now, there's a couple ways to do that. You can just get it at any time. You can just go through the list and check, or you can use what's called a priority queue and update the priority as you update the distances. So there's prime path. Should be reasonable. Alright, so now we do the multiplication game. So it says these two are multiplying an integer between 2 and 9. Or they start with 1, multiply by 2 to 9, and then you keep going. You draw an integer n from 1 to 4 billion. This is specifically 2 to the 32nd minus 1. And then you and then whoever reaches that number first wins. You take turns multiplying by numbers from 2 to 9. Alright, so I want to go over a few little things about this problem. So here's the thing. Your moves are multiplying by 2, 3, 4, 5, 6, 7, 8, and 9. So the initial state of this game starts with 1, and it's Stan's turn. Then Stan can make 8 different moves, and you can end up in 2, 3, 4, 5, 6, 7, 8, 9 at Ollie's turn, right? Now here's the thing. Now, some people might want to use a straight up dynamic programming solution to this, where you determine what the best move could be for a given value at n by dividing by these numbers and seeing what the worst move is in the previous run. See if you can leave them there. The problem with doing that is there are 4 billion numbers, and you may have to go all the way up. So the trick here is to recognize that the state of this game, or the number of states in this game, are very small. Okay? So no matter how large you get, so we know 2 is just 2, 3 is 3, 4, well, that's 2 squared. So that's basically like doing the 2 move twice. 5 is just 5. 6 is like doing the 2 and the 3 move at the same time. 7 is its own move. 8 is like doing the 2 move 3 times. And 9 is like doing the 3 move twice. So, essentially, you can uniquely identify the state of the game by how many of each prime factor is involved. And because we know that the number is going to be no bigger than 2 to the 32nd, we know that the counts on the 2s can be no bigger than 32. The counts on the 3s can be no bigger than, I believe, 21. The 4s can be no bigger than 16. And the not the 4s. The 5s, can be no bigger than 13. Or maybe, 13 or so. And the 7s can be no bigger than 11 or so. The way you do this is by taking the log base one of these of 2 to the 32nd. So you multiply these together, you get around 88,000 different possibilities, which is not that many. And so, in order to solve this problem, what I did is I just started from a given position and said, or I started from the beginning, and I said, okay, this is a winning position for Stan if at least one of the moves, this is a winning position for whoever's turn it is. It's a winning position if there is at least one losing position as a move that you can reach from here. Okay? And then the game ends if it becomes your turn and the number is already bigger than n, you have lost. Therefore, a situation where the game is already over, we consider a losing move or a losing configuration. So, with that being said, let's go to the code. So, I'll talk about this here in a second, because the way this code worked is they gave you just a list of numbers and had the end of input terminate the input. That's kind of tricky to do in Python. In Java, you just kind of read until the line comes back null. You can do while not EOF in C++. Anyway, so here's what we did. The main stuff going on here is in the win function. So win takes n. So the idea is win is going to return whether or not this current number is a winning configuration. So we're going to say win return, it takes n, it takes this p counts. P counts is a tuple of 4 numbers representing the number of 2s, 3s, 5s, and 7s in the prime factorization of the current state. Now, I used a tuple because a tuple can be used as an index into a dictionary, which is what this is. So I memorize the function, which means that before I return a value, I store that value in the memo, and then I go ahead and make sure that before I do anything else in the function, I check to see if there's already a value available, and if so, I go ahead and return that. This level, this was just in there for debug purposes, and I no longer need it, so ignore the level stuff. So, as I said first, the first thing I do is I check to see if I already have an answer. And you'll note that the answer only depends on the state of the game, the number of values of each prime. Then I check to see if 2 to the number of 2s times 2 to the number, or 3 to the number of 3s times 5 to the number of 5s times 7 to the number of 7s is greater than or equal to n. If so, this particular position, if you receive the go with that number as the current number, you have lost. Therefore, it is a losing position. We return false. Now, I have this. This is my list of moves, which is fun. This one represents 2, as it is a single 2. This one represents 3. This one represents 4, as it is 2 2s. This one represents 5. This one represents 6, as it's a 2 and a 3. This one represents 7. This one represents 8, and this one represents 9. And I go through for every one of those tuples, and I check to see if there is a losing position. So if not win with n, and then I call add tuples. What that does is it just goes through and adds, element-wise adds the values together and returns a tuple with those values in it. It's basically like vector addition. So I add them together, pass that in as the state to the win function, then I have the memo gets passed in, level again, doesn't matter. And then if we have some situation where, some move where we can leave our opponent in a losing situation, then we set it to true. And we return that. If we get through all of the moves and we haven't found a way to put our opponent in a losing situation, then this is a losing situation. And that's how the function works. You just do that, and then I read in the input. That's how you do it in Python. You say, well, you can actually just get a list of all the lines. If you say line for line in sys.std in, that'll just grab all of the lines coming from standard input. Then you can manipulate it as you want. Here, I had it go ahead and convert them all to integers. And then it just said for each integer, check to see if it's a win for the first player. If it is, Stan wins. Otherwise, Ollie wins. We're done. And it works pretty well. Solves it in half a second. All right. So, with that being said, I hope you had a good look at those. And, yeah, so we're going to go ahead and have another go this week. We've got, we're going to need to start putting together the teams pretty soon. And it may just be team at this point, depending on how many people we've got. But hopefully we'll get that going, and I will see you all next time. Good luck on this week's problems. See you later.